Is there anybody there? The person who's hosting, you're on mute. Can you tell me if you're going to host or? Can you hear me?
خلاص ان شاء الله ضبط. يعطيكم العافيه.
Hello.
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 Hello. Can you hear me?
Yes.
Okay. Jim Herndon.
Okay. You can start now.
Okay. Do I share my slide set, or have you got them?
Yes, you can share.
I'm going to share. Right. Okay. Can you see that?
Yes, you can come on. Yes.
Okay. Okay. I'll start then. Okay. Good morning. Good afternoon. My name is Jim Herndon. I'm the enterprise technologist for Dell. I cover EMEA, Europe, Middle East, and Africa for Dell as a data center power and cooling specialist. What's a green data center? Michael Dell announced this admittedly 3 years ago, but it still applies today. He wants Dell to be the greenest IT company on the planet, and we are driving towards that in terms of sustainability targets. So, this comes right from the very top in terms of data center sustainability and ability. So, definition of a green data center is a difficult thing. By its very nature, it consumes a fair amount of energy. The whole purpose of it is to run the IT with the minimum amount of energy and also the minimum amount of wasted energy. So in that sense, it's that's your goal effectively. No impact to the environment or minimal is another possibility. Again, depends how you build it, but certainly minimizing things like concrete and non-renewables is an issue. So we'll focus on this right the way through the slide set. hope you enjoy it. And any questions, I'll pick up at the end on the Q&A. So the challenges in the data center. You know, most of these I get fed back from customers probably 3 or 4 times a week. One of the ones that I always, for want of a better word, bang the drum about and speak about is customers roadmap their data center and their IT. You know, most customers have an idea of where their IT is going and what they're doing in the future. They don't do the same thing with their data center. And this means that you tend to make decisions that are maybe not as wise as they should have been. You know, they tend to be a bit ad hoc and made on, you know, on the fly. And by doing that, you're potentially making bad decisions. You should have a short, medium, and long term, and a very long term plan for your data center. What it's going to look like in both the near future and also the distant future. And, you know, that should, as it rolls out, be driven through as a plan. Certainly adopting, you know, removing old and dormant hardware and replacing with new is a valid point. Old hardware generally is inefficient. It's not giving you very much performance for its power consumption. So therefore, you're better off replacing it with new. These are some typical rules I use when I'm looking at the expanding data centers. The rack sizing is getting fairly important. We'll talk about the reasons why you need wider racks later. But certainly, I wouldn't be looking at designing a new data center or refurbishing the data center with anything less than a 1200 mil deep rack and a 750 mil wide one. Expansion's always difficult. Different companies expand at different rates. Typically, I tend to use 30 to 35% increase over the lifetime, 10 to 12 years. So that tends to be a good rule that's stood me in good stead over the years. Some companies grow by acquisition, so they may need a slightly higher number than that. I've seen companies use 50%. Certainly no false floors. A rack these days, a 42-year rack or a 48-year rack can go to either 1.1 ton or 1.3 ton. So your floor loading is far too high for false floors generally. And you get no advantage from that false floor. And obviously you need a fairly high ceiling level. 42-year racks, 2 meters tall. You're going to need another 400, at least 400 mil on top of that to clear the overhead feeds for things like water, cabling, power, etc. And again, minimum 1200 mil clearance at the front of the rack to safely load hardware. Hardware is getting deeper and deeper. We're getting close to 1000 mil for a lot of it now, hence the reason for deeper racks. And by the same token, you need that gap at the front to be able to load hardware safely. And in fact, 1400 mil is probably a safer, you know, basis for designing on if you're designing from scratch. So the main electrical feed to the data center is to power the IT, but we also need to deal with the heat from the servers. So cooling is required. Generally, most data centers, even HPCs these days, are fed by UPS, either in part or in full, and possibly then a generator, depending on the reliability of the supply and also how critical keeping the lights on for the HPC is needed. You also need lighting, security, and anything else that may make a data center work. That's things like IP cameras and things like that. So this is the basic energy feed you're going to put into the data center. So going forward, using the 80-20 rule, UPSs these days are extremely efficient. Typically, if it's under 4 or 5 years old, it'll give you about 99%, or it should do. You should be running something around there. From that point of view, your UPS losses are very, very low indeed. And you are probably, even by going for the latest and greatest, you're only going to get percentage points in improving that. So the expenditure tends to be, very long term. Lighting security. Lighting these days is LED, so it's low power, and it's typically switched by proximity switches. So when you go into the data center, it switches on. When you leave it, it switches off. If it isn't, then it needs reviewing. Security has been a fairly static power consumption for many years. Cooling still relatively power hungry, and this is where the wastage comes in. So what we're going to look at is how we can improve the cooling, because that's where we're going to get our biggest percentage wins. What's PUE? PUE is power usage effectiveness. I've also seen power usage efficiency used. I'm not worried either way. I was a member of the Green Grid. I still am a member of the Green Grid, and Dell EMC are a founding member of the Green Grid. So it's worth a look at the www.thegreengrid.org. There's some very interesting things on there, even if you're not a member. So PUE was originated in about 2008. It's simply a ratio. It's the ratio of your total facility power, which is IT, cooling, UPS, lighting, security, cameras, etc., divided by IT load. So you end up with a ratio. The closer that ratio gets to 1, or that number gets to 1, the better. You can't have 1. That's a physical impossibility. But you can get very, very close to it with modern technology. So just as an example, 100 kilowatt data center with 80 kilowatt of what's known as non-sensible load, cooling, etc., would have a PUE of 1.8, which Gartner still rate is the average for medium-sized data centers across the globe. Excuse me. So I converted all these numbers to Saudi riyals while I was doing this the other day. So a typical 750 server is going to cost you something around 1,300 riyals per annum just to run the server. You've not called it, you've not done anything else with it, you just run it in terms of energy consumption. So that's assuming it runs about 600 watts and also 100% utilization every day, for 24 hours a day. So that's the CO2 figure for those that look at such things. And the scary bit is that a PUE of 1.8, it's going to cost you around about 1,000 to cool it as well. So, all in, you're running 2,400 to actually install and run this server. You've not put any software on it. You've not connected it. You've not put any networking on it. So all you're doing is running the server. So fundamental physics, all of the electrical power you put into a server is converted to heat. There's a very, very fractional amount comes out as signal. So pretty much every kilowatt you put in comes out as a kilowatt of heat. So you need to deal with that. Our servers, as same with most manufacturers, take cold air in the front and exhaust it as hot air out the back. So we need adequate amount of cold air or cool air supplied at the front of the server. And when I say adequate amount, it is possible to have air of the right temperature, but not have enough volume to actually run it. So that's quite important. And also having a hot air removal path from the rear of the server and the rack is useful as well, because otherwise you can physically end up with stagnated air, and you end up with recirculation back to the front if you're not careful. So this is a quick graph that I tend to use when customers talk to me, or when our own internal people talk to me, of the technologies that I would be looking at. So most HPC these days is certainly up in the upper numbers, 8 kilowatts to 42 kilowatts, and then 15 kilowatts to 90 kilowatts. So you know, a lot of data centers are typically running around those sort of numbers. We've done projects recently, and we are working on projects that are running around 80 kilowatts of rack power. By going to GPUs, that's very, very easily achievable. So you know, these things need looking at. Typically, cooled rear doors start at around 15 kilowatts, although they can be used lower. Below that, generally, you'd use some form of in-row. And as they say, the elephant in the room is DLC. So Intel and AMD have both said that the future CPUs you're going to be buying cannot be air cooled. They have to be liquid cooled. So at that point, you need some form of a liquid cooling for them. So I've put on there greater than 250 watts. It very much depends on the server model, server design, and also the processor you're looking at, and also to a certain extent your infrastructure. But certainly you need to be looking at an overlay network of direct liquid cooling for future-proofing your data center. I had a look at the current Dell range recently, and we're currently on what's known as the 15th generation. And there's around about 30% of the servers that can be direct liquid cooled, depending on which processor you select. Going forward for the next generation, that looks to be closer to 50%. And for the generation after that, probably even higher. I can guess at about 75%. So certainly, if you don't want to be left behind, you need to have a DLC loop in your data center. So the trend is for rising power. It's also for rising performance. So for a lot of people, you're going to end up with less servers, less racks, but more power from those racks and more power consumption in those racks. As I say, an 80 kilowatt rack is probably not unusual these days. And certainly I can see it coming in the future. So you need to really, really look at the design of your data center. No longer can you plug in some sort of relative small amount of cooling and get away with it. The air needs to get to the right places properly. It needs to escape from the right places properly. So, you know, it needs a bit more scientific design than we've used in the past. So water is 4,000 times more efficient at removing heat than air. So that's a given. Older data centers, there are still some data centers around running 6 and 8 kilowatts, and they're probably going to have to adopt some fairly leading edge technology. Otherwise, they're going to be effectively left behind. So that enables you to keep up with the trends, meet future legislation. When I was researching some of the Saudi details earlier for this slide set, certainly looks like CO2 is something that's being tabled. And the other thing is to ensure hardware reliability. Overheating hardware fails miserably. So you know, if given your overall temperatures outside, you need to ensure that there's adequate cooling to keep the lights on and the systems running. So this is a piece of Excel I knocked up probably about 10, 15 years ago now, and it's still valid today. So this is a 0.5 megawatt data center. I'm comparing a PUE of 1.6 to a PUE of 1.3, and we're showing an energy saving of around 150 kilowatts. The energy saving in kilowatts per hour is very, very significant here. And there's quite a significant financial saving by being more efficient. So, you know, this is, by being green, you're actually saving money. So, you know, a lot of the senior management will probably look at it as more as, you know, as a money saving exercise than rather than a green one. Although obviously you can, you know, having the green thing, green bit box ticked is always good. I've used 0.25 reals per kilowatt hour. I know in Europe we're currently seeing massively rising power costs. I don't know if that applies to the Middle East, but certainly, you know, with rising power costs, the saving becomes even more significant. So as I say, this is just a quick and dirty piece of Excel as a calculator. So as I say, you're saving money by being green. New PUEs are around about the 1.2, 1.4 mark. We can get to that. You can go significantly lower than that, especially for bigger data centers where there's some, you know, advantages in sizing. So you can start using sort of some more leading edge technology, which is harder to use on the smaller data center. So, as I said earlier, heat density of servers getting greater. The big problem is, especially on 1U servers, is getting sufficient airflow through that 1U box. That's, you know, 1U is about 38 to 40 millimeters. So you've got little fans running very, very fast, which tend to be inefficient power-wise. The market likes 1U servers, unfortunately, or fortunately, it's you know, it's always been the case. So in terms of getting efficient airflow through them, efficient and sufficient is actually a challenge. So, and as I said earlier, Intel and AMD CPU total dissipated heats are going to get much higher. What is an 80 or 90 watt processor today will become probably a 180 to 100 watt processor tomorrow. So as we go forward, you're going to see the whole TDP numbers slide upwards quite significantly. Possibly for HPC, you're going to see 300, 400, 500 watt CPUs, which aren't going to be air cooled. DLC allows higher water temperatures, which also means less chiller infrastructure potentially, even in you know, the Middle Eastern environment, and also allows heat extraction and reuse from the outlet water. So currently we're looking at putting in 45 degree water into degree C water into this and getting out 55 degrees, which is ideal for things like underfloor heating. And in theory, and to a certain extent in practice, it enables lower total cost of ownership. So you're going to need less chiller infrastructure and the ability to reuse free air cooling as the water temperatures rise. So DLC, DCLC, direct liquid cooling, cold plate, they're all known as the same thing. I will use DLC right the way through this slide set, but they're all the same thing with different names and different buzzwords. So basically it puts a box, a hollow box, onto your CPU or whatever you're cooling, and you flow the liquid through it, and that then takes the heat away far more, as I said, directly than the air would. The Dell solution uses dry brake couplings. These are motorsport or aerospace standard, so they're very, very efficient, and you can literally break a joint, they bang it together, and all you get is a very, very slight dampness on the front, bit of condensation. Otherwise, it's completely dry, and they're certainly drip free. On our solution, you use a manifold within the rack. and this manages and merges all these water connections together. And on our solution, the pumping is done elsewhere. It's not done locally in the server or in the manifold. It's actually done at cold water distribution unit. And this is the reason for having wider and deeper racks as well, in that you will need space for these manifolds. So when you're looking at this, the manifolds go where the PDUs do. That limits your PDU numbers. You'll need less but higher power PDUs. So we are currently looking at 63 amp PDUs. I think they'll become the fairly new normal. So that gives you 43 kilowatts in a rack, 86 kilowatts if it's non-redundant. And then the next step up from there is 125 amps three-phase. Now that's probably, to use the phrase, a bridge too far for a lot of customers at the moment. But I can see that becoming, almost a default, especially for HPC. This is why the 750 mil or wider racks are going to be essential. You'll need a cooling water loop in your data center adjacent to the racks and the chilled water distribution unit. Now, the chilled water distribution units can either be end of row or they can be in rack, depending on your rack sizing. Generally for HPC, we would use end of row, which would run 10 to 15 racks, depending on power. And current water temps can be up to 45 degrees C, as I said earlier. So typically we do a 10-degree delta C across there. So your outlet water is 55 degrees C. Your chill water distribution unit uses glycol coolant on both sides. The low point, the freezing point is fairly high. So look at your data center closely. It could be costing you money. It almost certainly is if it's over 5 or 6 years old. And there's some advantages in going forward and getting some assessment done. They'll offer assessments. I frequently travel to customers and do data center assessments. And there's also going to be, pressure from governments to look at their CO2 usage overall. And data centers are reckoned to be about 2% of the overall consumption in Europe. And I suspect it's probably pretty much a similar figure across the world for a lot of it. So, it's going to be very much a focus point. It's the same as aviation, actually. So I can see this being very, very much a point of, view for the, the sort of people, the conservationists to look at. It certainly figures on their radar. Also, your customers will be aware of the numbers as well, so they'll be looking to see how efficient you are, especially if you resell time on it or whatever. And fundamentally, it's going to cost you money, if it's inefficient. So, as I say, with energy costs rising, you're going to get reliability by getting a better data center and also lower running costs. Thank you. Back to the host. Are there any questions? I can't see any on chat. Good morning, Martin.
Hi, Jim. Thank you very much for the presentation. Just a question regarding the direct liquid cooling. You were talking about CPU. Is there any plan for the GPU? Because, nowadays, most of the systems of supercomputer are using GPUs, which consume more power, I think, than the CPU.
Yeah, going forward, there will be a GPU option. Basically, it's cost effectiveness. GPUs, to a certain extent, memory and CPUs are very cost effective to DLC. The rest of the server isn't so much, and the returns are much poorer, basically. So from that point of view, so it's far more efficient to use air for that, than use a secondary method such as a cooled rear door to cool the excess heat off. But yeah, GPUs going forward will be water cooled, definitely, because they're going to become 600 and 700 watts. Any more questions?
Yes, Jim, this is Salih from Howard. Regarding
Okay.
the temperature,
Yeah.
you mentioned that we can increase the temperature to 45. What is the maximum that the ASICs can sustain without damage?
Depends very much on the product. So the whole point of the cooling loop is because you're removing heat a lot more efficiently. You can run at 45 degrees C. Currently, and I'll use Intel as an example here, is the junction temperature is around 90 to about 105 degrees C. Current word on the street from Intel is that that's going to have to drop in future. So it's going to probably come down to about 65 or 75 degrees C, and that may reduce your incoming water temperature numbers. So you may end up down at 30, 35 degrees C. Currently, some of our guys over in the US talk about 35 degrees C being the new normal. So that will still give you a 10 degrees delta T, but you're obviously going to need lower incoming water temperatures. So yeah, I mean, it varies very much product to product. Typically, as I say, it's junction temperatures on CPUs and things are up in the sort of the very high double figures. So yeah, does that answer your question?
Yeah, thank you.
Okay.
Thank you.
Any more?
Jim, this is Hussein again. What's your recommendation for those who have a data center, another data centers, and the maximum rack is 8 kilowatts? So what's your recommendation?
Well, one of the things we're looking at for a lot of customers at the moment is if you've got 8 kilowatt racks, which are fairly low, then by putting an overlay network on of cold water pipes, we can then add another 50% capacity. So you can actually go to 16 kilowatts, maybe even 20 by running DLC servers. It's still not great. You would be better altering the whole data center and doing a refurb to make the data center, more higher power. But certainly it gives you a short-term increase in your rack capabilities for the short term. Going forward, I mean, we're looking currently at 1,000 watts PU, 1,500 watts PU. So at 1,000 watts PU, your 42-year rack is going to be 42 kilowatts. So, if you're only running even at 20 kilowatts, you're going to end up with half full racks at best. So, it's going to be quite wasteful. So, yeah, I mean, looking at improving the overall design is quite significant. And I spend quite a lot of time with Dell customers doing exactly that. So.
Thank you very much.
I mean, I'm available if you ping the Dell team an email. They've all got my email address and contact details. So, if you've got questions, then by all means, let me know and I'll endeavour to answer them. Any more questions? I'll take that as a no. Good morning, Martin.
Can you all hear me? And shall I start sharing my screen?
Yeah, I'll stop sharing mine and I'll pass over to you. Thank you.
Okay, good morning, everyone. Or actually, for me, it's in the middle of the night, but that doesn't matter. Today, I want to speak about platform efficiency for large-scale workloads. I want to show you some of the work that my group has been doing at HPC Engineering inside Dell. And I would like to start off with what Dell, if it's working correctly, it isn't. Here it is. That's what Dell actually does in the HPC space. Now, what a lot of people don't realize is that Dell has been active in the HPC area for more than 20 years. So when we firstly had in the 90s of the previous century, all those expensive proprietary systems where everything was custom, from the CPU to the memory, the hard drives even had special firmware. Every vendor also had, because of the custom components, had its own operating system, its own compilers. So the whole space was very fragmented, you can say, and there was a lot to choose from. Now, then in around 96, NASA realized with Thomas Sterling and Donald Becker that perhaps a cluster of HPC PCs that were connected through a network could also be capable of running HPC workloads. So that is where the Beowulf cluster project was started. PCs connected through a standard interconnect, Ethernet back in the days. And the operating system of choice was Linux. So it was all open source and open components, so everyone could collaborate and invent on top of what they had developed at NASA. Now, as Dell, as one of the largest PC vendors in the world and server vendors, also saw that their systems could also run HPC workloads, and that is how we also got involved in Beowulf clusters, because of the nature that Dell does believe in open standards, not in vendor lock-in. So our systems could very easily be adopted to run HPC workloads, and that is where we actually started already in 1999 with our first HPC cluster installed at Cornell University. Yeah, it was in 2001 where we launched our solutions program. So today I'm still in what we call HPC or global solutions at Dell. So it's still considered to be a solution. And we offered our first solution bundle, and we still do that, by the way. Then we had a few systems in the supercomputing top 500, one at NGSA and one at Sandia National Labs. And it was around 2005, 2006, also coincidentally the time where, for example, YouTube was founded. It was the rise of what you can say the hyperscalers. So the Facebooks, the Googles, the eBays. So companies that rely on a very dense infrastructure for their daily business. So lots of compute, lots of networking, there are lots of I/O, and indeed very similar to HPC, you can say. And it was also around that time where we saw the rise of the hyperscalers, and we formed a special division called DCS that made custom data center products for those hyperscalers because they needed the density. Now, what then happens was that one of those solutions called the C-series server, and the C in that name stands for cloud. So we were very early already busy with cloud around 2009, 2010. One of the hyperscaler form factor servers became part of the standard Dell server portfolio. And we are now, I believe, in the sixth generation of those PowerEdge C series, with the next one on the horizon. Now, we merged with EMC for storage later on, because we saw that storage became more and more important, and that data management and data movement was going to become increasingly painful for a lot of customers. We also had, around that time, 2015, 2016, the largest vendor system in the top 500. So in our innovation lab in Austin, we still have a top 500 class system. So in 2015, that was the first generation. We are now at the fourth generation of this system, Zenith. Now, we have done a lot of collaboration with TAC, obviously, which is also in Austin, where we have the top 10 Frontera system together with Intel, and we still have with E&I in Italy the largest industry-based HPC system. So we actually do a lot in HPC. Now, the Dell message for HPC is that it's based on three pillars. It is about democratizing, optimizing, and advancing HPC. And what we mean with that is that with democratizing HPC, we want to enable HPC for everyone, so that they can work on science, on their engineering and their analytics work. And therefore we want to make HPC easy to use. We want to lower the barrier so that you don't have to learn a lot of low-level things, that you can just use HPC in your daily work to get things solved. We also believe that systems should be optimized for HPC, and I will talk about that a lot in this presentation. And we mean with that it's not only about the best performance, but we should also look at the best efficiency. And I think with the current energy prices, where Jim has talked about in the previous session, this is becoming more and more important, that we not only run the fastest, but we also run in the most efficient way our HPC workloads. Last thing is that we want to advance HPC. So we do that through providing expertise. We keep innovating on top of our products. We also believe that we should not invent the wheel ourselves. So we rely on partnerships a lot. And that can be in hardware, it can be in software, as long as it adds value to our HPC program, you can say. And this is true from the entry-level work group class systems, where you have a small cluster, all the way up to the top 500 class systems that have multiple racks of compute and storage. Now, what I do in the group where I work in, you see in the center what we call the HPC and AI Innovation Lab. That is a very large compute lab / server room in Austin. It is 1,300 square feet. What we do there is that we design and develop our HPC systems and solutions on top of that. We do that through creating reference architectures. We tune the systems for various HPC workloads. So, for example, if you have a Dell server and you want to enable the HPC system profile in the BIOS, which is there, that comes from us. So we do that. We turn every parameter on and off. We tear the whole system apart, and we make sure that it is configured most appropriately for HPC workloads. We also do a lot of R&D. So it's not only solutions engineering, but as said, through innovation, we also do R&D, and we do that together with our technology partners that I already mentioned, but we also do that with parties in the field. So we have collaborations with various universities, primarily around the world. They act as Dell solution centers for certain areas where we keep innovating HPC as a whole. We also do a lot of application performance studies, and that is what I am primarily doing, for example. So we look at how to run applications or workloads or mixtures of workloads in the most efficient manner. And we publish those studies online. So you can find on hpc@dell.com, you can find a whole list of white papers, blogs, presentations, best practices, test results. It's all freely available for the HPC community, and it's all around either systems or applications or networks and storage solutions as well. Now, we also work together with our CTIO office, where we look in the future, and we collaborate in designing and implementing advanced future technologies. You can visit the HPC and AI Innovation Lab. You can book a tour. We can give you technical briefings where we also bring in our distinguished engineers and Dell fellows on certain topics. And you can also get remote access to the Innovation Lab if you want to test drive something yourself. I mentioned the Dell Centers of Excellence already, and you see here various universities around the world with whom we collaborate on certain HPC solutions. So yeah, Cambridge is a prime example where we have been doing joint HPC research for, I think, over 10 years already. And so we have various centers scattered across the world that all work on various HPC related solutions together with us. So they test prototypes, they test solutions, and we make sure that with that joint collaboration, we all bring the HPC market forward. Okay, now switching to something more technical, where I want to show you some examples of the work that we have been doing inside HPC solutions engineering. And I start with some examples of MPI studies. Now, to start off with MPI, for who doesn't know what MPI is, MPI is the primary programming interface that allows us to use multiple systems for a single problem. So this is the heart in terms of software of an HPC/Beowulf cluster, you can say. So you see here 4 systems, 4 nodes that are connected through a network. So typically that is a fast and low latency network, because if the systems are going to collaborate, we want as minimal overhead as possible. Now, what we then do with MPI is that those systems communicate through what we call messages. So that is a software layer, and in that software layer that everyone runs, because they all have their own memory space, as I showed you in the previous slide, they are all standalone systems. Your data needs to be exchanged, and we do that through messages that we send between nodes. And if you talk about messages, then you can think of an express servers, also for MPI. So an express server, typically, if you send a parcel, then it contains a sender at the back. It contains a destination where the parcel needs to go to, and it contains a reference tag. So in case it is in transit, so think of your FedEx track and trace number. It's very similar to what MPI is also using. So when server A sends a message to server B, then that message not only contains the contents of the package itself, but it also contains where it came from, where it has to go to, and it has a reference tag to find out if the message is in flight. So it is on the network, you can say, whether it has arrived or not. So MPI is typically, your communication is typically your two-way. So you start with your one node, and that node then sends portions or sections of the data to individual nodes. They then work on their individual part of the data, and the result is then assembled and is sent back to node 1. So this is done through send and receives. So what you then do, node A sends, and node B then acknowledges that it has received the message through a receive message. Typically, 90% still use MPI, and of the HPC applications, and I don't see that yet changing in the near term, because the MPI standard as a whole still keeps being developed and innovated. So we are now at version 3.1 of the standard, and I think in a few years version 4 is actually already on the horizon, which has a lot of extra functionality for hybrid workloads, because what we are seeing currently that domain-specific accelerators, or your DPUs, are becoming increasingly important for certain workloads. Now, how can you tune MPI, and how can you make sure that you get the best performance? There are some functions in MPI, and we call those collective functions, that have a lot of overhead. And the reason why they have a lot of overhead is that they are called by all MPI ranks. So everyone participating in parallel communication has to call that function, and that function is then being used, for example, for a global summation, where all the partial results are being assembled into a big result, as I showed in the previous slide, or it can be used to find out what the global maximum is across all data. It can be used to scatter data. It can be used to do a matrix transpose, and you can tune those messages. Now, the thing is with those collective messages is that because everyone calls that function, is that what can happen is that a lot of time is then being spent in fixing what we call load imbalance. So what you see here is a area plot of the NEMO ocean modeling application. And you see here on the horizontal axis, the MPI rank number. And here on the vertical axis is the walk log time. So the green area is the time spent of the total walk log time of the run in the application itself. And what you now see very obviously is that some MPI ranks, so some cores of some node, have more work to do than others. And what you then see here in yellow and in red or purple are MPI functions and the time that it takes. So this is application in green. The rest is what we call communication overhead. And you can see, because of the extra time spent for these MPI ranks, that the MPI all reduce function, so where all those partial results are then being assembled back into a one big result. Because all the nodes participate in this function, that the other nodes have to wait until until the load imbalance is completed. So you see here very little time in MPI all reduce. Here you see much larger time in MPI all reduce. And yeah, actually same here, but here it is being done in MPI receive. I think that these are special IO ranks, so we don't take them into consideration. Now, what you then should do if you want to optimize these things that you for those collective operations, then you should look at modern functionality in MPI, and we can do what we call non-blocking collectives. So we can, instead of waiting until everyone is complete, we can just initiate the send and receive, so the collective operation, then do something else, and then at the end see whether everyone has received its data, and make sure at a certain point that that has to be completed, because we need that data. Now, what I mean with it is this. for example, take two cores. They are both running a computational part, which you see here, and you see immediately that core 1 has more work, has less work to do than core 2. So there is a load imbalance already. When core 1 is done and sends data to core 2 through an MPI send, then core 1 has to wait until core 2 is done with its computation and can post the matching received or the acknowledge of the MPI send, you can say. And this wait time is very power consuming. So what you see, if when a system is in an MPI wait loop, that it is consuming full power. And so when the receive is done, then obviously both can start then at the next computation. So let's assume that we have a core frequency of 2.6 gigahertz for both cores. Now, ideally, what you would like if I am doing my post, my send, that I have to wait, that I will do that in an efficient way. So let's say that I want to go to my load P state, then core 2 can enable its turbo mode, because this is running at a lower state, so there's more power budget available for other cores. So this computation here for core 2 can then be sped up through the CPU running in the turbo mode. And ideally, you could then have a potential speed up of the application. Now, another thing in the MPI reduce is that it is really killing MPI performance. So you see here certain workloads. So you see OpenFOAM, you see PAM crash, another CFD code, and a material science code. What you see are very large portions in MPI all reduce. You can say perhaps you should run it in a different way, but this is with lesser cores, but this is very, very common. So you see a lot of orange overhead, and the message size are all very, very small. Very hard, therefore, to optimize, you can say. And it is really killing our performance, because here we have more than 50% overhead. Here we have easily 30. I think this is 40, and this is also 40%. Now, if you then look at how fast an all reduce can be for a certain MPI library, then they are all pretty much the same. Except for OpenMPI, where you don't run hardware collectors. So you immediately see that depending on the message size, it doesn't matter much unless you run very large messages, then you will see the latency going up. Now, if we then take a look at this example here, then you see immediately here also a load imbalance because of the nature of the application, and you see MPI all reduced time on top of that. Now, if we then look at the all reduce in particular, then what we are seeing is that there are over 100,000 calls during the duration of the run, which is pretty standard, I should say. But all the calls are less than 64 bytes. And we also see that some MPI ranks spend far less time than others, and it could be up to a factor of 4. So the minimum time spent by one rank is 30 seconds. The maximum time is 4 times that number. Here you see another example, and I want to dig deeper here. The MOM5 ocean model, you see here also some load imbalance. You see the same MPI all reduce here in yellow, and it is really hurting performance. Now, if I dig then deeper into my MPI all reduce, what it is actually doing, and I distinguish between what I call the wait for the message to arrive and the actual communication. And I showed you in a previous slide that the communication overhead for a single all reduce is around 30 to 40 microseconds, you can say. You see that a lot of this overhead is caused by actual load imbalance. And the transfer time itself you see here, it is for this MOM5 benchmark, it is only 18 seconds out of perhaps 190 seconds or even 463 seconds. So you have a lot of overhead due to load imbalance. Why we keep, as HPC, your community, we keep looking at networks, at your solutions that have the lowest latency. Well, actually, there is also a far bigger cause of your performance loss, and that is load imbalance. So it's something to be aware of. And you can see when I zoom in that the blue part is very, very small compared to the actual load imbalance itself. Now, a thing that can help for certain applications is hardware offload. So if you have, for example, a NVIDIA Connect X6 HDR200 card that has an accelerator on board, and that accelerator on the network card can be used to run certain tasks for you on the network. So you can offload things that would normally run on the CPU. You can offload that to the card, and therefore, in theory, it could run much faster. Now you can enable that, and it's called hardware collectives. You see here for the 3 major MPI libraries how you enable that. And what you see then typically, if you're in VASP, for example, here, where you do a all-to-all, so a global transpose, what you then see is that the execution time, so that is your transfer time itself, that is in the darker colors. So you see dark green, you see dark red here, and you see the actual wait time, which is in light green and in light red / pink. When I then enable my hardware collectives, you see here on the right that my actual transfer time is minimized because of the enabled hardware collectives. So you see that the load imbalance doesn't change. So the light green and the light red / pink doesn't change, but you see here that the darker colors are far less. And what we have achieved by only enabling hardware collectives is a 20% speed up. So this is something that you can use for certain applications to really get better performance without having to change anything in your application. Something about InfiniBand, what has also changed over the years is that we now have far more cores. So let's say 10 years ago, where we had FDR, InfiniBand, 56 gigabits per second, with approximately a 1.3 microsecond latency, we had 16 cores per node. Now in 2022, we have 128 cores per node. We have HDR, so we have 200 gigabits, so 4 times the number of 4 times the bandwidth. But we have 8 times more cores. So I see that the per core bandwidth has been halved compared to 2012. You see here that latency now is well, has improved some, but not much, you can say. So what can we expect? So you see, indeed, what I said, 8 times more MPI ranks, but we have less bandwidth. So are we good? If you look from a latency bandwidth perspective, and I started with Connect X3, so my 56 gigabits, and I go all the way up to Connect X6, and I've also put the Omnipath in here. You see that the latency hasn't changed much. The bandwidth has improved some, maybe up to a factor of 4, as I said, for HDR200. Now, what has changed a lot in those 10 years is the message rate. So the number of messages that can be sent in a certain time frame. That is what we call message rate. And that has greatly improved over the years. And that is actually exactly what we need. So this is why you see that you still get very good performance from your InfiniBand card. It's not necessarily the latency and the bandwidth. No, it is that the cards can keep up with supporting higher and higher message rates. And this is important because if I look here at an AMD system where I have two 64-core CPUs, so I have 128 cores, you see when I run full MPI, so I have 128 cores enabled, you see that my message rate actually is the highest. And when I run on 64, my message rate is halved. When I run on 32, it is again half of that. So you see that my card is perfectly capable of sustaining messages that come from all CPUs. So I don't need to sacrifice anything there. For the bandwidth, obviously, it is different. So you see already that a single core, so if I run only on 1/4 of the cores, you can see that I am already able for larger messages to get line rate for my bandwidth. So this is actually exactly what I thought that it would do. Now this is very important. So if I run then, and if I look at my memory performance and I look at my bandwidth, then you see that if I go through various levels of cache, that obviously my L1 has the greatest bandwidth, L2 is less. For the L3, AMD has a higher bandwidth than Intel, and for memory, I've also measured a slight change in bandwidth. Now, why is this important? If we look at the memory bandwidth on a whole node, so we run your stream, what we do here, and we look at the total memory bandwidth, and you see, because of your chiplet design of the AMD, that I do not get good bandwidth for all thread numbers. So you see that there are spikes or number of threads that actually give good bandwidth. So you can see here on the AMD that I get maximum bandwidth on 16 cores, I get on 24 cores good bandwidth, on 32 and on 40 cores, and then it tails off a bit. So if I run then at 128 cores, then my actual totally available memory bandwidth is 30% less compared to what it is here. Now that is important, and I thought that I had a slide here, but it gives you opportunities to run hybrid workloads. So, for example, on an AMD system, what I mean, you shouldn't always use all cores for MPI, but perhaps it's a good idea to run with lesser cores and then use threading inside an MPI domain. So, for example, 32 cores times 4 threads each, where you still utilize all the 128 cores, will give you better performance because you have better bandwidth compared to if I run at full 128 core MPI. If I look at the power consumption of my MPI messages, as I already said, that can be very power consuming intensive. What you see here is a power consumption graph of an MPI barrier, so where we are all waiting for data. And you see that almost all MPI libraries run at full your TDP. So I have a Intel Ice Lake CPU at 205 watts. And during that barrier, where it is only waiting for data to arrive, it is running at full speed, consuming full power. And depending on the MPI library, the latency obviously varies. Now, some notable things. You see that my hardware collectives, that is my open MPI with HCall, actually lowers power consumption, which is what we expect because we offload things from CPU to the card. So we see that my system consumes around 10% to 15% less power when I have hardware collectives enabled and I'm inside an MPI barrier. Now, Intel, most notably, has done something very clever. So if you run Intel MPI and you run an MPI barrier, then it is not consuming 205 watts. It goes down to 150. So you see here that Intel has worked very hard in reducing the CPU power consumption for an MPI barrier operation. For the all-to-all, so where every MPI rank sends to everyone, you see that that doesn't differ much between MPI functions, because this is the most data and compute intensive operation that you can think of in terms of MPI. You see that everyone runs at full TDP. So this is an area where we at Dell very actively are looking into to see whether we can optimize this. Okay, something on applications, and I'm around 35 minutes. Okay. Another thing that we do is that we try to look deeper inside applications. So what we do is that we sample the performance monitoring units of a CPU using internal tools for that. And with that, we look at the behavior of HPC applications. So what you see here are 3 graphs for a WRF simulation. It's a 72-hour forecast, and I'm sampling here 10 times per second. And by doing that, and I look at my IPC rate, so my number of instructions per cycle, I look at my flops, so my floating point operations in terms of gigaflops this is, and I look at my memory bandwidth, then I can actually see all individual timestamps of my WRF forecast. So you can see exactly how my workload is behaving, and that it is constantly doing the same every single timestamp. And I immediately see that my IPC rate is quite low, and then at some portions it jumps up all the way. But I also see that that is combined with where I am using very, very little memory bandwidth. So it could be that I am doing I/O here. It could be that I am doing some communication between the ranks. And you also see that my application is very memory bandwidth intense. It is around 200 gigabytes per second. Whereas my flops rate is only 1/10 of what my floating point peak rate is. So you would say WRF memory bandwidth flops are not that important, and my IPC rate is also quite low. We also look at the power consumption. So for example, if you have an AMD system with your chiplet design, then you can measure the power consumption also of all individual cores. Now that is something that I've done here, and this is, I believe, HPL that I'm running here, and you see that my CPU, which is a 200-watt CPU, it is consuming full TDP for the whole duration of the run. Now, when I look at the power consumption of my individual cores and I add them up, you see that there is a large gap. So the total product or sum, sorry, of my power consumption of the individual cores doesn't match what I measure in terms of TDP. And this gap, what you're seeing here, is the gap or the extra power consumption done by the I/O die. So the I/O chiplet of my AMD CPU, it's the L3, it's a SOT, it's the HGMI socket fabric, etc., etc. So things that are not core performance or power consumption related, but all caused by the I/O die of my AMD chip. And for my WRF application, it's even more. So you see here the same behavior that I showed in the previous slide per timestamp, and you also see here that there's a much larger gap in terms of what I'm measuring on a socket level versus what I am measuring on a per core level. I also look, and this is also WRF, I believe it's the same workload, where I've looked at the L3 hit rate. And if you know the AMD chiplet design, where we have two 64-core chips, they both have 8 compute dies, so also 8 level 3s. So in my dual socket system, I have a total of 16 L3 caches because I have 16 compute dies. You can see that on average during the run, that my level 3 hit rate is around 60%. So that is that solid bold line here, around 60%. Now, if I run the same workload on an Milan X, where I have 3 times larger L3 cache, you see that my hit rate is not 60%, but it is up to 74%. So it is much higher, and exactly what we also expect to see. My performance improvement was around 12% because of the larger L3. And when I zoom in, you can see the same behavior again in terms of my time steps. And you see here for the Milan X, you see that my hit rate is really much better. So you see here a very prime example where you can use or should use a Milan X CPU instead of a normal Milan CPU for this workload. Now, the extra bonus what you get is a decrease in memory bandwidth. And here we have sampled all the memory channels of the system. You can see on average that it is around, it's hard to see, but it is, if you calculate the average, it is around 200 gigabytes per second that I'm measuring on my Milan X system. Actually, it is much lower. So because of my larger L3 hit rate, my memory bandwidth goes down, which is good because this means that perhaps now if I go forward and I only run this kind of workload, that I can perhaps save power on the memory fabric. I could tune down the clock, yield more performance to the CPUs, or I could perhaps use single rank memory, which is cheaper because I only need to sustain less memory bandwidth compared to my normal CPU. We also look at GPUs where with our low-level tools, and here you can see, if I start at the first graph, you see a lot of dots, but actually when you zoom in, and what I have here is an NVIDIA, is a Dell XE8545 with 4 NVIDIA A100s. And I am looking at the host to device bandwidth. And you can see here also all the timestamps again for my DFT simulation. And you see that that I have 4 GPUs, so I have 4 different colors with a memory host to device bandwidth of around 4 to 5 gigabytes per second sustained. And even when I zoom in further, you can really see that my host is not always transferring data, but obviously it is doing some transfers. Then the GPU is busy, then it does another transfer, etc., etc. We also look at how we can predict performance. And what we do for that is that we look at the roofline model. And what the roofline model is that we try to express system performance as a function of floating point peak performance and memory bandwidth. When we combine peak performance, so flops, with memory bandwidth, then we get something that we call arithmetic intensity. And arithmetic intensity here is how many flops we can get out of a single byte of your data from memory. So obviously, when I get a lot of flops per byte, then I have a very arithmetically dense system. So that is typically your BLAST3 matrix multiplication function, or your particle methods. FFTs are less arithmetically intense, and the worst or the least arithmetically intense are stencil methods, typically done in reservoir simulation, or where we have sparse operations. For example, in your CFD, you typically see that you see very little flops per byte. And why is this important? I always say all isoply written code is ultimately memory bound. So you will always at some point hit a memory bandwidth barrier because there's always only so much that you can get out of your application. Now, why is this called a roofline? Because if we then combine your flops rate with the arithmetic intensity in flops per byte, and we do that on a logarithmic scale, then you get the slope of a roof, because here our performance is being limited by the memory bandwidth, because we can only get so much flops out of a certain number of flops per byte because of the memory bandwidth. When we get here on the right, then our limit is the floating point peak. We can never get more than a certain gigaflop number out of our CPU because of architectural limits, and the same is true for memory bandwidth. So if my application measures here, then I say it is memory bound. When it is here, then it is compute bound, and I can optimize my application from being less memory bound to more compute bound by, for example, do better use of caches, or I can improve here to get closer to my floating point peak by doing micro optimizations in my application. So if we start on a sunny day, as I call it, for the roof, then and I have my AVX 512 in case of Intel Ice Lake, then you see here that this is the whole blue area is my capability of my CPU, all the way to 4 teraflop here. If I cannot do AVX 512, but I only have AVX 2, then my floating point, your throughput halves. So I don't get 4, but I only get 2, or here a little bit less. So you see less potential performance, but in general, it is still quite okay. Now, if I cannot do AVX2 because I cannot do an FMA operation in my application, then that the floating point bandwidth halves, because I cannot do 2 operations in one cycle but only 1. So standard AVX, then it is not 2, but it's only one teraflop here. So you see it is down to 1/4 of my AVX 512 peak. And it becomes worse because if I cannot effectorize and I fall back to scalar instructions, then this is 1/4 already. So you see that my performance potential is very, very low. It's not 4 teraflop anymore, but it is here, what is it? Less than 256 gigaflop. So I am losing a lot of performance potential. And if I cannot do what I call instruction level parallelism, where I can now only use one floating point pipe, you see that it is even half that number. So you see why it is important to optimize your application. You see that otherwise you are leaving a lot of performance potential behind. Now, this is what it looks on an AMD Milan system, where I have a bandwidth here. So my memory bandwidth determines the slope. I don't have AVX 512, but because of my many core system, I have a good floating point peak at 4 teraflop. My Intel Ice Lake has a slope that is not as steep as my AMD. It is a little bit less, but the floating point peak is around the same due to AVX 512. So you see that I more or less have the same capabilities. And then when we look at real applications, where we then measure the flops using that tool that I showed you, combined with the arithmetic intensity, you see that, for example, my OpenFOAM CFD application is totally memory bound. It is approaching my memory bandwidth limit here. So this is useful because if I measure directly, I'm seeing 200 gigabytes per second. So you think, oh, it is not fully saturating the memory bandwidth, but actually it is because of the low arithmetic intensity. So I am indeed hitting an architectural barrier of my system with this application. WRF is also, as I said, quite memory bandwidth dependent. There are some parts of the code that are not. There are also some parts that are quite efficient because I get quite high up in the on the roof line, you can say. And this is things that we do at Dell to get better insight in how applications behave and where architectural limits actually are if we want to run systems like this. Okay, I have 10 minutes and I want to conclude with a case study where I look at a full wave inversion application. Very common in seismic processing. And this is a 3D automorphic time domain full wave inversion application. It was hybrid MPI and OpenMP parallelized, written in C and using FFTW and BLAS. So you could think, okay, this is quite well written, good performance potential because it is using hybrid OpenMP for best bandwidth compared to threads, and it is using optimized libraries for certain operations. We ran on 60 Dell PowerEdge servers with a Dell Ice Lake system. So if we then compile here, and we use your standard your compile options, what I've done, so I compile for AVX 512. Then what I get is that my loop doesn't factorize. My compiler says that there's a vector dependence that prevents factorization. And the reason is that there is a dependency between these two arrays. When I then looked with an Intel tool at what my application was actually doing, and I don't need to do all ranks, but I can only do one because with MPI applications, typically all MPI ranks do the same type of work, but on different data. What I see here in my advisor outputs that everything was scalar during the duration of the run, and there was very little factorization in my application. So I thought, okay, let's see whether I can fix the vector dependence, because I can tell the compiler that it should not worry about the anti-dependence of these arrays because they don't overlap. I know that, and I tell the compiler that by enabling the fno alias flag. Then my loop indeed factorizes. So I get here a message that my P loop is factorized because it wasn't aligned on a boundary. So it firstly had to peel until it was aligned. And you see here that I get a nice speed up of around 2.2 compared to my scalar code. But I also get a message that there were 10 divides, which are very CPU intensive in terms of instruction latency. And there were type conversions, which are also quite expensive. So my fno alias flag adds 20% of extra performance because I enable more factorization compared to my starting point. Okay, then I looked at my type conversions, and what I saw here were things like this. So here I'm, for example, assigning a value to two variables. My code is single precision because my arrays here are single precision data, so 32-bit floating point. But when I'm assigning a value of 2.0, that is a double precision value, not a single precision. So that means that it has to do a type conversion because I am assigning a double precision value here in a part of this product to these two variables. So I have to do a type conversion, and I need to convert this down. So the fix here is to say that you do single precision by adding the F suffix single precision floating point data. And the same was true not only for operations like this, but also for a lot of intrinsics. So my sine and my square root and my absolute value and my exponent, they all have single precision implementations as well. So if you run single precision, make sure that you call the single precision function of that. Another thing was where around what I call implicit branches. So here there was in my triple nested loop, there was a condition here every time. So what you then can do is that you split the loop in 3 pieces and therefore removing all those conditions. So I just do it 3 times, which is far more efficient than having to do a branch for every single value. And at the same time, what I've done here is that I have removed a division or 2 divisions already here. I placed them outside of the loop. It was also where my compiler was complaining. And what I get indeed is around 50% factorization with acquired good factorization efficiency. Now, and the final step is then, if I look at my timeline where I started with a performance of around 400 seconds, and you do all kinds of things, sometimes even worse because you try things. Then what was the real trick was to do my loop splitting that I showed you to get rid of that condition inside the loop. And then at the end, you can see there are fewer micro optimizations that are possible, and you end up with a 2 times speed up of your application performance compared to your starting point. So you see that some effort, and this obviously does take quite some time, but it can really pay off to look very closely at your application and how it behaves. And lastly, here is then the roofline of my standard application and my optimized application in yellow. And you see here that there are more data points to the right. So I am getting more arithmetic intensity. And I also get a slightly higher percentage of my floating point peak. So you can also see that in the roofline that it is working as I thought that it would. That concludes my talk. It were a lot of topics, but I also had an hour yet to cover. As said, if you want to know more about what we do in HPC, then I can really recommend you to visit our community page, delhpc.org, where you will find a lot of information. You can also here, for example, find out when our next HPC community meeting is. It is on the Monday in the week of supercomputing. You can still register there if you want, again at delhpc.org. If you want to know more about what your group is doing, then go to the HPC engineering page at hpc@dell.com or the info hub. Do you want to know more about the Innovation Lab or what we do with the Center of Excellence, then you can find it there. Thank you. Are there any questions?
Thank Martin. I have one question. Sometimes when we get performance, it also depends on the memory layout and how you place the data in the memory. And there are more cache hits, sometimes more cache misses. So will it affect the performance of the loop splitting?
In the last section, I already made sure there were a lot of threads. So in this case, there were 60 MPI ranks, and so one MPI rank per node, and then you had 32 or 40 threads per node. So the placement then doesn't really matter. It only matters if you run with a few MPI ranks and your threads. Then you also want to make sure that the threads are as close to each other as possible. So typically you bind to a NUMA domain, so that you take the whole memory layout into account.
Okay.
To get best cache usage and memory bandwidth, as I also showed in the stream peaks. So for AMD, for example, it is very important and to place your threads as close to each other as possible to get the best memory bandwidth.
Right. So thanks, Jim, and Martin. With this, we will conclude the session. I would like to thank the audience, all the participants in the hall. So thank you very much. Looking forward to have a similar session next week in the Saudi HPC. Thank you, Martin.
You're welcome. Bye-bye.
Martin? Right, we'll be having a next workshop in a few minutes. That will be the workshop 5. It is from the HPE, Hewlett Packard Enterprises. The title will be Cray AI Development Software and Environment for HPE Supercomputing Workshop. So HPE has their own supercomputer environment, and the speaker will be Andrea Carboni. So he will be going to start in a few minutes. Thank you very much. You can have some refreshments, please. But don't forget to come back in after 5-10 minutes. Okay, we're going to start. Maximum 5-10 minutes. We can move another one. Maybe he showed him picture, maybe he will see somewhere. Yeah, come down to the workshop. Okay. You will see the picture on the yes. Come, run this is the book. Yeah, it's around. Okay. Here? No, I don't know. Hey, how are you?
Pandemic
Yeah,
confined us to other places.
how is your father?
No, my father's good.
He was missing you. They do ask to come and visit him. They come here as well.
They prefer me to come there. This is workshop 5.
Yeah, I'm looking for the speaker. So just going to take 5-10 minutes break, and hopefully we'll start. You can sit in. You're the boss.
Not really.
You are. You can. So we're going to start in a few minutes. Speaker is here. I will be having 1 hour session, and then we will go for lunch, kind of refreshment, and we will start again around 12:30. So it will be a 2 hour session, first 1 hour, and then again after refreshment, 1 hour more. Yeah, we'll play one now. So you hear, and I'll ask you which one is go. Okay.
Do I need to put
Yeah.
content here?
It's okay. You can use the USB, or we can try yours.
This is online. You need to
Live stream.
Yeah, I need. Okay, let me take the speaking.
Running. Just in case. Yeah. If there is no demo, we can use this. Slides.
I copied the file, but
Just minimize it, maybe.
where?
Copy. This will be right.
Yes.
Copy. Can I copy both on the desktop?
Yes, if you also
You
have
don't-
PDF, you can copy both. Okay, and I also need a browser. for the demo.
One more just in case. Google. Google. Demo.determined.ai 88. Yeah.
Okay. Okay. We are almost there.
We're running parallel sessions, so there are other workshops.
Mm.
So 3 more happening.
Okay. We can start.
Then there are also.
Okay. Thank you for joining this workshop. I'm Andrea Carboni, and I am an AI solution engineer for Hewlett Packard Enterprise. Today, I'm presenting you what is our flagship product in terms of machine learning and deep learning. So let's just start with the key values that the product has, because those key values, key points are the needs that the customer has when they start their journey into the machine learning. So the first point, the first need that the customer has is the cost, trying to cut the cost. Because when we have, when a company starts to use machine learning in a very efficient way, they have trainings that go 24 hours a day, 7 days a week, and it is a continuous model training and retraining and refinement. So when a company has some models in production, it is not just having one model trained and then wait some days for other stuff and so on. Your hardware, the customer hardware, is used all the time. So in this case, it's very important to cut costs. And in this case, an on-premise solution which is dedicated to the training is the best solution, because here we can have nodes with a lot of GPUs. We have Apollos with 8 GPUs, but we can have also in the newer products 16 GPUs for each host. And all those nodes are interconnected by a very fast InfiniBand network layer. And this is very important also because when a model is trained in a distributed way, it is important to keep most of the work, most of the training inside the same node. And when there is communication between nodes, that communication must be efficient. And in this case, the cloud environment is not very useful, because a cloud environment is useful when you need the resources on demand. So you need 10 GPUs, you go there, you get 10 GPUs, and when you have done, you release those GPUs. But when a company is in a real production, the cost of having each GPU 24 hours a day, 7 days a week is very, very expensive. And an on-prem solution is very cheap compared to these cloud environments. Also, the time. The time is another important aspect during the journey to machine learning, because a company wants to make money. A company wants to be on the market as fast as possible. And how a company can achieve this? One way is to accelerate the training, accelerate in the fastest possible way, because when a machine learning engineer develops a model, there is a sequence of trial and errors and tuning of AI models. And when a model is training, the machine learning engineer is basically idle. So we want to reduce this. And to reduce the time needed for the training, we have to distribute the training, distribute over 100, 1,000, or even more GPUs. And after the training, you get a reasonable good model, but you don't get the best model. In order to get the best model, you have to optimize all other parameters that you used into your model. And here we have an algorithm that now is proven to be one of the fastest on the market. It has been developed by some PhD students that were then hired in HPE. There are abstract and also evidence that the algorithm is very, very fast. And the third point is user collaboration, because when a company sees that there is profit in using AI models, there is an increasing number of team members. And the more team members you have, the more it's complicated to coordinate them and to make them productive. So the user collaboration is a very important aspect during the machine learning journey of a company. Okay, let's see now what happens when a company wants to start the machine learning journey. In the first day, there are some explanatory or exploratory works and activities. There is just one machine learning engineer, maybe two. Each engineer has its own laptop with a GPU, making experiments, and things are pretty easy. But when the model is completed, is tuned, is trained, and the company was to move into production, it is normal to increase the team size. And with more people, you have more frameworks, because each engineer is more like to use one framework instead of the other. Someone may use TensorFlow, others may use Keras, and so on. And here, one important aspect is the resource management. In the first case, I have one user with his own GPU. That's fine. But when I have 10 people or 20 people working on the models, maybe the same model or not, how can I provision the resources? I need to provision a lot of GPUs. And for each GPU, I need to understand if that GPU is used or it is free. Because assuming that I'm a machine learning engineer and I want to run an experiment, I want to train a model, I need to know which resources are free. And there is a competition between me and other colleagues. So it is important to have an automatic resource management. Also, there are other aspects. As soon as the model increases in size, one GPU is not enough to contain it. And when more GPUs are needed, when more hosts are needed, because all GPUs inside the same host are not enough, it becomes difficult, because the machine learning code must be enriched with infrastructure code. And in the end, a machine learning engineer finds himself writing more infrastructure code than machine learning code. Okay, so what happens now? A few companies may have enough resources to build from scratch their own infrastructure. And in this case, the infrastructure becomes an asset for them. But for all the other companies that do not have high resources, they try to combine different open source projects. In the AI field, you may find a lot of components and products in the open source world, especially on GitHub. But it is difficult to combine them. You can find one component dedicated to one aspect, another component dedicated to another aspect, and in the end, putting together and have those components working is difficult. So here we were able to combine different aspects, the infrastructure management, the user collaboration, the hyperparameter optimization, all those aspects together into a single product. This diagram is just to show you the purpose of the product. The product does training. It can do training in the most efficient way. It allows you to optimize your hyperparameters, provides user collaboration capabilities, but it is focused on training. And it also provides open points to connect other components. So, for example, on the left, you can find the data storage components, which creates sort of repositories to store the data sets. We have simple object storage like S3, HDFS, but also Pachyderm, Spark. With Pachyderm, we have an integration sample on the GitHub repository. So it is possible to store your data set into Pachyderm, leverage the pipelines that Pachyderm provides in order to trigger trainings and retrainings every time new data is available. And on the right side, we have the inference set of components. So you have your model. Your model now is great. It has been optimized. We want to serve predictions. So in this case, we have other capabilities. For example, MLflow. Seldon is one that we considered for an integration example, which you can find on GitHub together with Pachyderm. It's a complete end-to-end example. But the product, the machine learning development environment is focused on training. You can train on-prem, you can train on cloud, you can train on bare metal or on Kubernetes environments. For example, on cloud, it leverages the auto-scaling capabilities. So you probably know that on Google and AWS, you can create instance groups where each group is a set of machines with GPUs. And as soon as new experiments needs to be trained, new machines are created on demand, on the fly. And when the training is completed, those machines are automatically removed by the cloud provider to save costs. Okay, let's switch to the demo. Okay. So I'm showing you a demo on object detection. The network is a faster RCNN with a ResNet 50 backbone. And we are training using the Penfudan pedestrian dataset. Okay, so this is a typical code that a machine learning engineer will write in order to train a model. You can see that it is a set of train and evaluation for a given number of epochs. When this process ends, we have a good model, let's say. But we have chosen two specific values for our hyperparameters. And we want to optimize searching for all the space where those hyperparameters are defined. And the typical code that a machine learning engineer will write is this one. The same process, train and evaluate inside two nested for loops. In this way, we can scan all the domain for the hyperparameters, and in the end, we may get the best model. So, what is missing from this approach? The first one is of course, the distributed training, because the code just performs a single training, and if you want to perform a distributed training, you have to add a lot of infrastructure code. The second point that is missing is a parallel search. You see that two for loops nested one into the other has a high complexity, and all the trainings are done sequentially. We want to do this in parallel. If we have a lot of resources, we want to do this in parallel. There are other aspects that are very important. One is the intelligent checkpointing. If we consider large models that now are the main stars in the machine learning world, I'm talking about DALL-E, GPT-3, those models. they are huge. A GPT-3 model with roughly 50, 70 billion parameter inside is around half a terabyte. So, you understand that when an experiment is trained, we don't want to save all checkpoints, but we want to save checkpoints only when the new model is better than the previous one. And this saves space, but it also saves time. You can imagine saving half a terabyte on disk for each checkpoint, how much time it will require. And in addition to this, a large model, I take usually the case of GPT-3 because we have some numbers. The training can require 1 month, depending on the number of GPUs used. I saw it being trained with 250 more or less GPUs. It may happen that in 1 month, 1 GPU goes down. Actually, in a customer, maybe they had some problems with NVIDIA. They had 3 or 4 GPUs broken within 1 month. So it is important that the training process does not go into the error. And it is important to resume the training. And the final important aspect, of course, is experiment tracking, which is under the user collaboration topic. Because there will be many users working on different models, or maybe even on the same model. And I want all information related to an experiment. I want to know the code. For example, if I need to take the model created by someone else and I want to maybe do some experimentation, I must be able to reproduce exactly the same results that the other colleague got in the past. I'm talking about not only the code, but also the generated logs and all other metrics, the training metrics that the model may produce. This is important. So let's see how we can run experiments on the machine learning development environment. We will use the determined package. I will go over this point later, but the machine learning development environment is the enterprise version of the determined AI open source software that you can freely download, install, and check without any constraint. The workflow is a user working on their machine, standard laptop, with the Python editor, creating the code. When the code is ready, the code of the model, there is a command inside the determined package, that command, that is used to run experiments. So in this case, let me show you. Running the that command from command line, we simply create a new experiment into the cluster. You can see 2 main points here. One is the const.yaml file, and the other is this one. The dot here represents the current folder, the folder where your model code is. And in this case, the code is on the left side, the left panel. Okay, we run this command. We have a new experiment run into the MLDE platform. Let's see. Okay, this is our experiment created 1 minute ago. Let's dig into it. You can see here single. This is a single training, no hyperparameter optimization. It is still active because it is training. Okay. We have several tabs. Where the platform will display the metrics, the model metrics. The metrics are just defined inside the model. Each engineer can define their preferred metrics. In this case, we have object detection, so we have the where is the average value of the intersection over union. We have the list of hyperparameters. They were presented into the configuration file. We have the code that has been submitted. It is taking a little bit longer. Okay. So all files inside the package that has been submitted to the master node are there. You can examine all files and the configurations. We have the logs. Those are the logs generated. And we also have some metrics. We can run the experiment with the profiling enabled, so we can see the performance. Here we are managing images for the object detection. So the speed of the system is roughly 1.3 images per second. We can have other metrics. For example, we can see the time spent in different sections of the code. So, for example, the time spent in loading the images, the time spent to send data to the device, to the GPU, the time spent to get back results from the GPU, and so on. And also we can have other metrics more system-oriented, like the memory of the GPUs. In this example, we have just one GPU. Here we can see the free memory. This is very important when you train a model, because different GPUs have different sizes in terms of memory, and sometimes a GPU can fail the training because the memory is not enough. Now, let's go back to our notebook. I want to show you the configuration. Okay, this is the configuration file. It is very short. There are a few parameters here. One is the name of the experiment that you may want to see on the user interface. Some generic parameters like the source of the data. The hyperparameters here are listed in this particular way. I will show you why. And a few other configurations. This is important, a slot per trial. We are specifying to use just one GPU to train the model. Let me spend a few words on the environment. The platform runs experiments using containers. So you can use every combination of frameworks that you may need. We provide by default an image which provides PyTorch, TensorFlow, Keras, that you can install extra dependencies if you need, or if you need a completely different image, you may build that image and just use it into the experiment. This is an example for the demo. I'm just using a predefined image, purpose-built for the presentation. Okay, now let's see our API. So we have our experiment for 6.8. When a user installs the determined package, they get not only the that command, but also the SDK. So it is possible, like in this case, to connect to the server. Here, there is no need to authenticate because I'm running inside the notebook. But of course, with an external system, you have to specify the IP of the cluster, the credentials. The point here is that with the API, you can just connect to the cluster, downloads an experiment checkpoint. For example, in this case, we downloaded the best checkpoint, top checkpoint that was found so far, and then try to run a prediction. Let's see. Okay, not so good. Of course, the results vary depending on the initial weights for the model and also the number of epochs that we use. In this case, for demo purposes, we do not train for longer epochs. So the results may vary. Okay. Now, let's move from one GPU to 4 GPUs. Let's run the experiment so it will start. As you can see, the model, the dot here, remains the same. When you want to move from one GPU to 1,000 GPUs, you don't need to change the code. What we change is the configuration file. This is the file. Almost identical from the previous one, which was this one. So it is almost identical. The only difference is this one. We changed one number. And what happens? The experiment is submitted to the master node. The cluster is made by a master node and a set of agents. At least if we install on bare metal, if we install on Kubernetes clusters, we have just the master and one pod for each experiment. The that command will create the package with the all model code. It will send it to the master, and the master, looking at the slots per node, will start checking available resources availability inside the cluster. So on cloud, it may need to spin up new virtual machines. When the nodes are found and inside those nodes the GPUs are available, the master starts each agent inside the experiment portion inside each agent. And all code related to the distributed training is done at this stage, and it is completely transparent. The user does not see this code. Okay, this is our experiment distributed. It is still active, as we may see here. On the chart, we have only just one value in the end because we set the validation only at the end. The important points here are on the profiler side and on the logs side. On the profiler, we see an increase on the output. We now have roughly 3.2 samples per second. It was 1.3, if I remember well. And here we can see all agents. Now actually agents are configured with 8 GPUs, so we have just one agent. And we may see the metrics for each GPU that is currently training our model. So we can select one, and as before, we can select some different metrics like the memory and so on. The training is going on. Oh, it is completed. Okay. Another important aspect are the logs. When you run distributed training, you may involve 10 nodes, 20 nodes, 100 GPUs. Each process will generate logs. And it is important to have those logs centralized somewhere. And here you can see it is very similar to the logs we saw 30 minutes ago. Now there is a difference. Here, the rank. The rank is the process. So running the training on 4 different GPUs, we have 4 ranks. And we have all those logs centralized here, and we may filter on the rank, for example, just to focus on some logs. Okay, let's go back to our notebook. Okay, we got our model. Maybe reasonable model. And now we want to optimize it. optimize the hyperparameters. How can we do this on MLD? You see, it is the same. The that command, experiment create, a configuration file, and a dot. Again, we do not change the code. And how can we achieve this? This time, the configuration file is a little bit longer, just because we are now defining the hyperparameters in a different way. So, for example, the weight decay has a fixed value, but the learning rate and the momentum do not. Here, in this case, we are defining the domain. For the momentum, the minimum value is 0.7 to 0.95. And for the learning rate, we are using a log scale from 10 to -4 to 10 to -2. What else? We are defining just one slot. We will have different experiments in parallel, and we may choose to increase the slots used by every experiment. It is just a matter of not saturating the cluster. And here we tell the system to run an optimization. The mode is aggressive. It is not single. If you remember, it was a single on the experiment. Single here, single, those are single experiments, single trainings. Now it is aggressive. It is using our adaptive ASHA algorithm. You are not limited to the adaptive ASHA. You can select random search, grid search, but of course the adaptive ASHA is the fastest. And we can also define the maximum number of trials to run in parallel. I will show you how it works. We want to optimize our model. We want to run in parallel the optimization. So let's see how the adaptive ASHA works. We selected 24 trials. Okay, the algorithm will start with 24 trials in parallel. Each trial will receive a small portion of the data set. Very small portion. Why? Because we want from the beginning to filter out the trials that do not produce good models. So as you can see here, those trials here did not produce good models, and they were discarded. On the top part, we have other trials that with the initial portion of the data set produced a model that is worthy to be trained again. And those trials are promoted to the next step. So this is the second step. Now the trials that survived are trained with another chunk of the dataset, bigger. You can see here the length of this line is smaller than the length of this line, which is smaller than the length of this line. So every time the models are trained, some of those are just dropped. And in the end, repeating this process until the end, we end up with one to a few models that the platform was able to find out. Here, the configuration is built for the demo to just show you in a clear way how it behaves. But there are other settings to cope with models that needs more time to train. The configuration may be tuned to get the best from the algorithm and to address all different model cases. Each one on one GPU. But if you have a cluster with 10 GPUs, the system will run 10 experiments in parallel. But each experiment will use just one GPU.
All of them running parallel.
Yeah, not the same, different GPUs. Each trial will use one GPU. 24 trials means 24 GPUs. If you have a big cluster, those 24 trials will run in parallel. If you have a cluster with, let's say, 10 GPUs, only 10 trials will run in parallel. When they complete, the remaining 24 minus 10 are scheduled to run. Okay.
Just to clarify this, let's say there are two parallelization methods, one for the hyperparameter and one for the training. You're saying here you're parallelizing the hyperparameter. Are we also parallelizing the training process itself?
If you want, yes. If you want, yes. Not in this case. This case, the experiment, the optimization is meant for the demo. So actually it runs for a couple of hours. So we usually do not show the progress, only the results. But as you can see, here, the search. Slots per trial is 1. We can put 10. And in this case, with the 24 trials, we will use at the same time 24 multiplied 10, 240 different GPUs. Okay.
Okay, and just to clarify, if you want to parallelize across GPU, did you come up with your own library, or are you going to use the NVIDIA library that does parallelization?
No, you don't need this. Actually, from the code point of view, there are two different approaches. One is to use our API and writing just some glue code. You can run the experiment using the backend. The backend does this automatically. Because on the backend, you may have different engines. One may be Horvath, the other may be DeepSpeed, and so on. With the trial API, that is automatic. If you have special needs, if your model is complex and it is difficult to port to the trial API, there is another API called the core API, which has been introduced 6 months ago, if I remember well. And you can just take your model, put into the cluster and run. Of course, if you want to integrate with the cluster, you have to write some code to export the metrics and see the metrics on the user interface. some code to save and load the checkpoint. Because if you take your model and just run with Python, run the code, the product does not know about your code and cannot add the infrastructure code to run distributed training, for example. There are two different aspects. I can show you more details just after the presentation. Okay, this is just how resources are distributed with the hyperparameter search. Depending on the number of slots that are required, the master can spin up different agents with different GPUs. We can support agents with 8 GPUs, 4 GPUs, 2 GPUs. Now, let's see the model registry. Now we have a model, a very good model. We want to register this somewhere because we want to download that model to make some inference. We want to work with that model. The experiment just creates the model. And we do this with our model registry. We can take the experiment ID, for example, no, this is the old one. Okay, let's go here. This is the distributed training. We got one checkpoint. And we may want to register this checkpoint to one of our models. We already have some models. We can choose the pedestrian detection. Okay. Version, you can specify the version, but it is also automatically generated. Register. Okay, now if we go here, here. This is our pedestrian detection model. This is just a container where we can put different checkpoints. The latest checkpoint was registered just now, as you can see. The version has been automatically added 31. And using the SDK, we can download the model by name and try to provide some predictions. So you can see here the code to do the same using the API. But let me switch to the presentation because we are going out of time. Okay. We have a different version of the product. The first one is the software-only version. That is what you saw just now. It can work basically everywhere, on cloud, on-prem, on virtual machine, on Kubernetes. This is the software only. Then there is the machine learning development system in the middle. This is a turnkey solution. So it is made by the software and the hardware. The hardware is our Apollo's 6500 each one with 8 GPUs. We now support NVIDIA, all different NVIDIA flavors, but we are going to support also other accelerators very soon, like AMD, GraphCore. There is also some work with the Cerebras. There is a lot more work here for the different accelerators. But now the solution, the machine learning development system, is shipped with the NVIDIAs. Depending also on the size, usually it is the NVIDIA A100 with the 80 gigabytes. And each node is interconnected with the InfiniBand network layer for the fastest possible training. And finally, we have also the software version. It is the same as the first one, but with a connector in order to run workloads on Slurm. This way, it is possible to mix HPC workloads with AI workloads on an HPC cluster. So, as I already mentioned, the machine learning development environment is the enterprise version of the Determined AI open source software. Actually, from the code point of view, they are the same. What the enterprise version provides you, in addition to the open source, is of course the premium support and some connectors to manage users. So connectors for OpenID Connect, SAML, this kind of capabilities. But the distributed training, the hyperparameter optimization, experiment tracking, user collaboration, all those features are present into the open source version. So what happens is that many companies, just for curiosity, starts with the open source version, and then they later may switch to the enterprise version, depending on the needs. Being based on an open source version, of course, we have a community. The community now on Slack has more than 1,000 different active members. Also, the product team is on the open source Slack channel. So every time you ask a question, there is a high chance to be answered by one of the engineers of the product. And on GitHub, there is a lot of code. The code of the Determined itself. There is also the working with Determined, which is another repository free of access, where you can find different integration possibilities and a lot of sample code that you can start working with. Thank you. Any questions?
So if we consider the network, the neural network architecture as a hyperparameter, it should be like the number of hidden layers and the number of processes. Does your software help you with that, with the architecture?
You mean network neural architecture search?
Exactly. So to determine number of hidden layers, number of nodes.
Yeah, more or less, yes, because you can build the model using a parameter that could be in a hyperparameter. But I know that you can go even deeper. I don't know how to do this now. There is some work, some developers did some code in order to provide the real neural architecture search. But now, from what this is just experimental. Now, what the product provides is the possibility to change the number of hidden nodes, the number of layers, and using the values as hyperparameters. This is possible. Any other question? I may show you briefly the code. Okay. Just to provide you with another overview on how a model can be ported to the trial API. Actually, this code is may seem a lot. There is a lot of extra code here. Basically, what an engineer needs to do is to extend the PyTorch trial class or the TensorFlow Keras trial class. And after extending the class on the constructor, you just need to create the model in the normal way. After you create your model in the normal way, there are just a couple of lines, extra lines that you need to add. One regards the optimizer. The optimizer is wrapped into a proxy object. And the other is to wrap the model. Wrapping the model allows you to export the metrics and all other information that is needed by the user interface. That's enough for the model. Then you also need a couple of methods to tell the system where to find the dataset. Two methods, one for the training dataset, the other for the evaluation dataset. This way you can connect to any source, you can connect to an object store, to Pachyderm, to a shared area, and provides a data loader so the system is able to fetch all the samples, the dataset samples. Then there is the train batch, which contains more or less the standard code that you already know. The only two steps which may be different are those for the backward pass and the step of the optimizer, because the optimizer has been wrapped. And the evaluate is very, very similar. You see a lot of comments here. So just to recap, if you want to port a model to our trial API, you have first to choose between the PyTorch, TensorFlow, Keras classes, create your model the usual way, just adding a couple of lines at the end to wrap up the optimizer and the model itself. Tell the system how to get the data, the dataset, and then write a small portion of code in the usual way for the training and the evaluation. And that's it. This way, the system is able to get the metrics, the logs, to other infrastructure code for the training and so on. Any other question?
I have a question, not on this topic, when you're offering for AI plus HPC. Is it seamless, or is it static to the point that if I want to run HPC and AI, Slurm and Kubernetes, can I dynamically slice up the cluster between them, or do I have from the beginning to say this is AI, this is HPC?
You can, on Slurm, you can create different queues with different priorities, of course, and map each queue inside the resource pool of the system. So, for example, here, this is a cluster running on AWS. We have just a couple of pools. One is the auxiliary pool, which is for tasks that do not need any acceleration. And there is the compute pool, which is the real pool with agents and GPUs. But we can have also many other pools. One case could be when you have machines with different type of hardware. For example, 10 machines with an expensive A100 GPUs and cheaper machines with K80 GPUs. And you can define two different resource pools and use the most expensive pool when you need that pool, and leave the cheaper pool to experiments that are not important, for example. Or there are other combinations. One typical combination is to have an on-prem resource pool and another pool on the cloud with a dynamic creation of nodes. This way, most of the capacity will be on-prem, and the extra capacity can be taken from the cloud.
I understand that, but I still don't understand if I can submit AI jobs and SQL jobs to the same queue, and then, because I can use GPUs for HPC, I can use them for AI. Right now, I don't see a software that allows me to dynamically run both AI and HPC. You have to predetermine and say, this number of nodes is for AI, this number of nodes is for HPC. Will you help in that regard? Will you allow Kubernetes and Slurm to talk to each other to the point that I can dynamically?
No, this is not possible now. Even because there are different constraints in terms of the scheduling.
Do you ever see that issue being resolved?
No. Any other question?
Thank you very much.
Thank you. Thank you.
What will we cover in the second hour?
The same.
Okay. The second session, the same.
The same, yes.
So it's just a repetition of what you have mentioned.
Yes.
So, about the development environment.
Machine learning development environment.
Yes, this is it. This is the development environment.
Yes. Yes.
So it's by the internet or it's cloud.
Yeah, we are working on a cloud version. Which
Is there like a desktop version? Because I try to go to determine AI. There's like a lot of codes and I don't understand.
No, now you have to install it. This version actually is the open source. It is not the enterprise. You need to install somewhere on cloud, on prem. We are working for an as a service solution, but it is still alpha.
It's still until now itself.
It is alpha. Yeah.
And it's all about the HPC, the AI, these things.
Yes.
So it's codes in Python.
Yeah, you can use Python. It's the main language, of course.
I can use any codes, any code.
Yeah, because you have a container, and running the container, you can run any kind of language.
So this environment, it will be easy for me to know the statics for each program I do or what?
I didn't understand that.
This environment right now, you just run it across, and there's like the statistics for each GPU, the statistics for the slots.
Slots.
Yes, the single slot, and there's like the 4 slots. Each GPU was, but the main software itself, it's already like from outside.
Yeah. Yes. You
And-
provide
and-
the
yes.
code.
And to connect it, I use the diff and the determine codes connected to this environment.
Yes.
Good. So it should be for me to add these things in my codes in Python to connect it with this environment cloud or from this.
Yeah. You need to have the environment somewhere.
There are tutorial, maybe he needs a.
There is a lot of tutorials and documentation. For example, if you go to this is the home page for the
Yes.
open source version, and you have a lot of
This one.
documentation. Yes, exactly. So there is an introduction for developers, how to install the.
So I want to ask you this quick start on these things. I download this link, which is compressed file. They found this. Is that the installation way or?
That's correct, but you need a cluster. Now there is no cloud version,
Okay.
so you have to install even, for example, on my machine, I have a virtual machine. The code can run with containers. There is also the documentation there. With Docker, you can spin up the master and one agent locally. It requires 6 gigabytes of memory. It's not depending on the technical codes that you may want to do.
The GPU memory or the.
If you have the GPU on your laptop, you can leverage it.
Oh,
You have to install some Docker packages, but you can.
also, I can use this development environment and open source in this Kali Linux and Linux operating system.
Yeah, it runs on Linux. It uses containers. So,
Content.
but the containers are specifically designed for Linux.
Great to meet you, Mr. Tabo. Thank you very much.
Thank you.
One more
You're welcome.
question. This environment only works on Cray? So on any cluster.
yeah.
So as long as you have this installation form, you can run it on. So if I have access
You need
to
the Linux, basically.
Linux and access, if I have access to GPUs and clusters, I can run it in
It runs on Red Hat, on Ubuntu, because it is just a container that is all package, simple package that is installed.
I see.
Very easy.
It's easy to, yes, I get it. Good. I'll try it.
Yeah,
Okay,
sure.
very interesting topic. Thank you very much.
You're welcome.
Thank you. Thank you very much. Do you have a LinkedIn page or something like this to connect with you in the future?
Yeah. You can find on LinkedIn as Andrea Carboni.
I'd love to find that company with SP tools. Committed.
Yeah.
There's- solution. Yes. Yes. Everything in the connection.
It will arrive.
Yes, it will arrive. I'm actually interested in this topic. Actually, I wrote an article about the super intelligence theory, which is hypothesis for now, but it's good. Like the deep learning and also the machine learning can help us to find.
Yeah, one of the main advantages is that when you want to run an experiment, you don't have to mess with the resources, the infrastructure, with the setting up the GPUs. So it is easier compared to what you have to do manually without it.
And also the idea of parallelism, the parallel running, which is I take right now operating system course, and they tell us in the course it's not defined until now, the parallel program, but it's actually here.
Yes, yes. It is an amazing topic.
So wish you all the best, Doctor, inshallah.
Thank you.
Good, thank you.
Thank you. No, the second workshop will be the same.
When you will start, you will debate it or not?
At 1:15, I think.
Can I take a picture from the presentation from the laptop? Yes, because from it's not easy.
Yeah.
Cool.
Hi, you have workshop here? Yeah.
We can start now, but the audience.
So I just want to grab something to eat in that.
What about 5 minutes, maybe? 5-10 minutes.
I knew 1:15 was the,
Yeah, 1:15.
I think. I don't know how much flexibility we have.
Change. Okay, so then we have time till 1:15. You can come around 1:15 and we will start.
1:15.
Yeah.
Okay.
Thank you. Okay, you can have a break.
I got just this email telling about the one workshop. I was not aware. On one.
That's okay.
I arrived just in
Yeah,
time.
done, yeah, we're done. Because you send the email and then I saw you were there. He is the one. So I just came out to welcome you.
Okay.
Just check, we start refreshments. One. But then you have lunch after the workshop. So we have lunch together. Keep it involved in this. Yes.
Do you see attendance table?
No, I think it was here. Someone took it. And they are going to play. So we'll start at 1:15 after 15 minutes. We start again, so someone will come.
No.
Okay. We'll give them certificate and you also your certificate will come through email, I think. So we'll give certificate to everyone. It's certificate like they attended this.
Okay.
It's an appreciation. For the call.
And do we have the recording on YouTube?
I think it's live. It's a
Oh,
live
live.
streaming, live streaming. So anyone who wants to join live, they can see.
Okay.
We-
I thought it was recorded.
Maybe, yes, check. I think recorded can be also. By default, it should be recorded. I'll check. Students, I think they do record all the sessions. But this one must be recorded because it's going online, live. So it's there. Now we are going 2 workshops and live viewers, no one more. We are going. I don't know how they do it live, maybe people will get an option, you go this workshop or this workshop. Both are running live.
And do you know how many people are following from?
I didn't check because I didn't check now how many students are now attending. But we have been told that a lot of places like this, students are attending. Some we have other female students, they couldn't come, so we have arranged similar things. So if you see like one person is one person, there may be there be big classroom like this and all. Normally, in the first time we are going to hear it like continent here in the kingdom. Separate. I'm from Pakistan, but I work here as a professor. So now things are opening before it was partition. Some people, students are not comfortable. We arrange privately. You can maybe questions can come from live and from their place.
I didn't get. Let us see about questions from live.
Didn't come, no, ask question.
Live, you mean from internet?
No, I'm going to ask from Mike or something. So you have a question, but people are very shy, they will not ask. Very unlikely that someone to ask.
Here I got
Okay, that's good.
4 questions.
Right. They are bored because they can't hear. Those who are shy, they will not come. They'll come to work. Maybe they'll see you with lectures. But maybe they'll not want to leave you. Or they are shy to speak. That's good. Someone understood your word.
And there was a student very interested.
One who is a handicapped, one who is very
The one
he's handicapped, he can't. He comes under support.
I accepted the invitation.
I don't know the name.
Okay.
Bushra, I think. Bushra is one of the students club member. I think she's coordinating with the virus team. So now you want to know. I think one, yeah, we got some requests from other place. They couldn't come to employees and they wanted to have a link. So we have sent them the Zoom link. I shared the Zoom link and also the live stream. Then they have joined this from. And they're like, so the Aramco place. And the last session, you can hopefully build up. So far things are going well in control. We had a big session first day and second day. Today we don't have topic, just workshops. So we are at peace. Oh, let me bring this. If there is anyone written outside, I will ask them to come. Okay. Here. They're coming in at 1:15. We'll start.
Okay.
Yeah. They're gonna be difficult, you know, you can't get good picture.
Okay, can I wait two seconds?
I think, yeah, but
I don't know how.
minimize it, just minimize. How do this?
So I don't know, this is.
Yeah, just minimize the. Or check them. Okay, it's good. Okay. I think you can maybe play again
Oh, it's not, the,
quickly. Coming and going. I don't- Yeah. Same thing happened. Is it written now? We will finish around maybe 1 hour, in 1 hour, right? 45 minutes.
1 hour.
Yeah, I did that. We'll start lunch around 2:15.
Okay.
Then if you are. They're finished at 2, so I think you will finish at 10 time, but in case you want to see the time, you can come downstairs.
Okay.
Someone will be here.
Nice, Friday.
Probably did asking very basic question. So we were just venturing into the area of deep learning, machine learning. I'm more into a context of computing and networks. So it's kind of, I'm trying to get into this so I can merge and perhaps do some additional research, like interdisciplinary research. So my question really is, what do you think is better? Should I get a high machine, or should I subscribe to something online in terms of getting like a GPU cluster? Because I'm looking at Macs at the moment. I think Mac Pros, the latest version, they offer somewhere around 10 GPUs to use and 16 GBs of RAM. Not sure how much the RAM is going to go.
Do you run a large experiments?
Yeah. Yeah, somewhere along the line, I do. Yeah.
How many GPUs? Roughly. RAM, one.
I may start with 10, but then obviously as the data increases, yeah.
And you plan to run jobs 24 hours a day, and
It will depend on the experiment, to be honest. The network data that comes in, I guess, is dependent on that. I'm just trying to gauge like what would be the best option for me. Should I subscribe? Because I know that there are certain subscriptions available online. Or should I just get myself, invest myself, like get myself a proper machine for that?
well, if you look in the long term,
Yeah,
probably the buying the machine is better.
okay,
Especially if you need to run workloads for
Yeah.
a lot of time.
yeah,
Because if you subscribe, probably it's better, easier to scale.
mhm.
But the cost.
That's what I was thinking, the scaling part. So I was thinking that maybe if I just subscribe, I'll be able to scale the GPUs that I need. But again, I'm to my difficulty.
Are you still in the early stages?
I am, it's not exactly, I'm not into that high-end data at the moment. I should be there in like, I don't know, years time perhaps.
Okay, because 20, no, 10 GPUs, is pretty expensive. So if you plan to have a sort of a data center,
Mhm.
some place to put more machines in the
Yeah.
future,
Mhm.
okay,
Okay,
would be a viable option.
okay.
But if you don't have such space, probably a subscription is better.
Okay.
Because you need the machines, you need someone to take care of this machine.
That's exactly, yeah, that was another thing I was worried about.
Okay, if you don't have touch keyboard, it's
Mhm.
better to go with a subscription
Subscription.
to avoid a lot of issues.
Yeah,
Maybe not only management, but also if there is some spread.
Yeah, yeah. And if it were to be, for instance, in the lab, I'm not sure I'm gonna have 24/7 to 24/7 access to it. So that was another concern I had. I was thinking maybe an online subscription would give me that access as opposed to buying something or maybe requesting the college to get something in the lab.
Maybe just be difficult to say.
Yeah, I do understand. Well, I am kind of in a dilemma myself, so that's why I thought maybe I should ask you about it.
Probably a subscription is better because probably you need some flexibility now. And,
Yeah.
After things are
Stable.
yeah.
Then I can have a better idea. Isn't it? Yeah, that makes more sense. Yeah. Oh, okay, thank you so much.
You're welcome.
Okay, I think we can start. So thanks for joining this workshop. I'm Andrea Carboni, and I am an AI solution engineer working for Hewlett-Packard Enterprise. Today, I will present to you our flagship product for AI, the machine learning development environment that allows you to train your model at scale. So let's start with the key points of the product, because those key points are also the needs that a customer has when they start a journey into machine learning. So the first need is the cost. Keep the cost low. This is an important aspect because at the beginning there is some experimentation, but when one or more model starts to work on production, probably the customer will end up in training their models 24 hours a day, 7 days per week. So after an initial experimentation, the usage of a cluster for training models is a non-stop. So it is important to keep the cost low. And we have found that an on-prem solution dedicated to training models is much cheaper compared to classical cloud solution. Because on cloud environments, it is easy to get new hardware, it is on demand. You can take a GPU, you can give back a GPU, that's fine, that flexibility is very useful. But when you need to get a GPU and have it working all the times, the cost on a cloud provider becomes very high. And on-prem, we can build dedicated architectures to train models. The second need for a customer is the speed. So when a customer has a model in production that they want to retrain those models pretty quick, they want, when they have new ideas, they want to achieve the market as soon as possible. And in order to achieve this, it is important that the training process is the fastest possible. This means to use distributed training, but not only this. You may imagine that the creation of a machine learning model is an iterative process. So a machine learning engineer starts creating the model. There are several steps of refinement. And when the model is training, the machine learning engineer is basically idle, waiting for the training to stop. And this time is wasted. So for this reason, we need to accelerate the training and to accelerate the way the best model is achieved. For example, through hyperparameter optimization. The third need of a customer is to have their users to actively and productively collaborate each other. So user collaboration, when there are 10 data scientists or 20 data scientists, becomes a very important aspect, because each one needs to work on models created by other colleagues. And it is important that every model is tracked down, not only to the code, but to any other aspect. So let's see from day one what could be the journey of a company on the machine learning. On day one, typically there is some exploration. So there will be one or two users trying to create models. Each user will have its own laptop with a GPU, probably. And things are easy, because each user just keeps track of what he does. So there are no problems here. Also, the infrastructure The user has his own laptop. But after the first model is created and after a company sees some profit from deploying the models, the team grows. And when the team grows, when we have 10 people working together, maybe on the same models, things start to become complicated. Because with the 10 or 20 people, we need some sort of infrastructure. We need a cluster of GPUs. And we cannot expect that each user knows which GPU is available and which one is currently allocated. We need some sort of infrastructure management. Also, several users may use several different frameworks. Someone can like TensorFlow, others can like PyTorch, and so on. And in addition to this, when the training demands more than one GPU, usually the machine learning engineer needs to add some infrastructure code to the model. And in the end, they find themselves writing more infrastructure code than machine learning code. And this infrastructure code just initializes the system, distributes the workloads to different nodes, to different GPUs. It is not real machine learning engineer work. So in the end, there are many problems when many users try to work together. And one problem, besides the users' allocations, there is also the experiment tracking, which is part of the user collaboration topic. And the more users we have in a team, the more important is this part. So at this point, there are two different kinds of organizations. Some organizations have a lot of resources, so they can afford to buy hardware and create their own infrastructure. For those companies, like Facebook, like also hyperscalers, the infrastructure becomes an asset. But for the majority of other companies, which do not have such resources, the only possibility is to combine together different components that are available, for example, especially on the open source community. You can find a lot of work, a lot of components. Each one may be dedicated to some aspects, one dedicated to training, one dedicated to user collaboration. In the end, it is difficult for a company to put those components together and have them working in a seamless way. And here we have the machine learning development environment, which is based on an open source software called Determined AI, which brings together all those capabilities. So the pillars are the infrastructure management, which is automatic, the distributed training, which can leverage from 1 to 1,000 and more GPUs, the hyperparameter optimization in order to get the best model as quick as possible, and user collaboration, all inside a single product. This diagram is just to focus on what the product does. It does training. You can use it to create the best possible model, but it is focused on training. And for this reason, in an end-to-end pipeline, we usually have other components. Components on the left that allows to store the data set We can have basic object stores like Google Cloud Bucket or AWS S3 Bucket, HDFS, but you may also find some components on the open source ecosystem like Pachyderm. For example, Pachyderm is very useful because it is a sort of GitHub for the dataset. So instead of storing the code into the repository, you store the dataset. And on the serving side, after we have the best possible model, we want to run prediction. So we need to link the machine learning development environment to other products. So we have MLflow, Seldon. Seldon is a component that we have integrated so into the GitHub repository called works with determined. There is an example of integrating MLD, machine learning development environment, with Pachyderm and Seldon. It is a nice integration because as soon as you receive new data into Pachyderm, a pipeline is triggered that creates new experiments on MLD, training or retraining models. And when a new model is available, it is automatically deployed on Seldon to serve inferences. Okay, now let's start a demo. Okay, so for our demo, we have the object detection use case. We are going to train a faster RCNN neural network with the ResNet 50 backbone, and we will use the PET-Fudan dataset for the training. Now, let's consider a machine learning engineer without any help from a framework. So, a machine learning engineer typically train a model, will run a for loop with a set of model training and evaluations. And after a given number of epochs, the machine learning engineer will get a reasonable good model. But he got a good model, he didn't get the best possible model. So, because the model is linked to the hyperparameters that he chose. And the next step would be to repeat the same training process, but this time inside two nested for loops. So with those for loops, we scan all the possible hyperparameter space, training a model for each combination. And in the end, when this process ends, we may reasonable have the best possible model. But what is missing from this picture? The first point is the distributed training. If we have large models, we want to accelerate the training because it requires a lot of time. Also, you see that two for loops, one inside the other, training a model is just a sequential process, which requires a lot of time. We are looking for one model at a time. We want to do this in parallel because we want to save time. There are other aspects that are missing. For example, intelligent checkpointing. The checkpoint allows you to save your model when you arrived at a given number of batches, for example, or when a metric is good enough. But we cannot save every model. We cannot checkpoint every model. If we consider some large models now there is a lot of hype on the large models, large natural language models like GPT-3, like DALL-E. There are many of those which provides very incredible capabilities. Those models are huge. For example, a GPT-3 model with around 50 or 70 billion parameters inside is around half terabyte. So you understand that saving half terabyte on each checkpoint is a waste of time and also a waste of space. So it is important in this case to have a platform that saves checkpoint only when the model on that checkpoint is better than the previous one that we have. Otherwise, it does not make any sense. And again, taking the large model example, the training can take 1 month or even more, depending on the resource. And during this time, there could be something going wrong. A GPU may broke. I saw a customer with 3 or 4 GPUs broken in less than 1 month. So we don't want to spend 29 days in training and the last day a GPU breaks and we have to throw away the model. We want the possibility to continue the model, to train the model when something goes wrong. That is very important. And another important point regarding the experiment tracking is the possibility to store any aspect of a model in terms of code, in terms of logs, in terms of generated metrics, because many users may work on the same model. I could work on a model created by another user, starting experimenting with new parameters, for example, and I need to be able to reproduce exactly the same results in order to start working from that. And we get all those capabilities with the machine learning development environment. How do we operate with the platform? The platform is installed in a cluster with a master and a set of agents. A machine learning engineer will work with their laptop. They create the model on their laptop using Python, an integrated development environment like PyTorch. Someone uses Visual Studio Code. When they are ready, they can submit the model to the cluster for training. And this is done with a simple that command. The machine learning engineer will install the SDK, which is the Determined SDK. Determined is the open source name of the product. The machine, I will come back to this later, just to anticipate that the machine learning development environment is built on a proven open source software, which is Determined AI. So we install the SDK. After installing, we have the that command, and with this command, that experiment create, we can create a new experiment. Let me start an experiment. So while it is running, I can show you some capabilities. You can see that there are two aspects during the training. One is the configuration file, and the other here is the dot. The dot represents the current folder, and it represents the code. Basically, all files present into the current folder will be brought together and sent to the master. Let's see the configuration file. The purpose of the configuration file is to drive the training and to remove from the code what should not be there, like parameters, hyperparameters, stuff like that. The configuration is very simple. We have, for example, the name of the experiment that will be visible on the user interface. We may have some generic parameters, like the source of the data set. We may have hyperparameters, which are defined here, because having them here allows for the hyperparameter optimization. I will show you. And a few other configurations. One important configuration is this one, slots per trial. One means that I want to use just one GPU. Okay. So with this simple configuration file, it ends here. I can run an experiment. This is the experiment I just created 3 minutes ago, still active. Single here means a single training. I'm not asking for any hyperparameter optimization. And let's see some details. We have, of course, the metrics. Let me show you even this one, the loss. The metrics are defined inside the code, so they are not hard-coded. Every model can define and export any metric. In this case, we are using the intersection over union because it is a normal metric for object detection. We have also the list of hyperparameters here. The code that we submitted, file by file. The profiler, this actually have to be activated, and it is useful when you want to see if there are bottlenecks into the training process. So on the profiler, we can see, for example, the samples per second that we are currently using. We are using images, so this is roughly 1.3 images per second for the training. Then we may see the time required by each part of the training. So the time spent here, the data loader, the time spent in getting the images, getting the data. the time spent in the real training process, the time spent sending data to the GPU and getting data from the GPU, and so on. We have a lot of metrics. And we can also go into the detail for the GPU related metrics. We are using just one GPU. And we can see, for example, the free memory. The free memory is important because some models need more memory, and after you start the training, after some time, the GPU may fail because the memory is not enough. And also the logs. All logs generated during the process, the training process, are here. Coming back to the code, actually, yeah. You can see environment image. Each experiment is run inside a container. So this means that you can choose any kind of framework, and if by default the system provides a container image with TensorFlow, Keras, PyTorch, but if you need special dependencies, you can install on top of the provided image, or you can create your image from scratch. There are also some images, for example, with NVIDIA Rapids that you can use. And this is the submitted configuration. Then there is also the runtime configuration, which is much bigger. Basically, the system writes down all defaults that were used when the experiment was submitted, because we want to be able to reproduce the experiment, and the system will save every aspect. All defaults are here. So in the future, if you want to replicate the experiment, you can. Okay, let's go back to the notebook. We submitted our experiment. Okay. So the experiment was 470. When you install on your laptop the SD key, the determined SD key, you not only have that command to run experiments, but you also get the SD key to interact with the cluster. So here is an example. In this code, I'm connecting the cluster. I'm using a Jupyter Notebook now on the cluster, so I don't need to specify the IP or credentials. But if you connect from your laptop, you have to. And with a simple API, we can get the experiment, get the best checkpoint, and download the checkpoint locally. You see here, we have a new folder, checkpoints, with the content of the checkpoint. And now we can try to run a prediction. Let's see what we have. Very messy. Actually, the experiment for demo purposes is run just for a few epochs. So results may vary and usually are not very accurate. Okay, we submitted our first experiment. Now we want to distribute this experiment over a number of GPUs. How can we achieve that? As you can see, it is the same. That command experiment create a configuration file, distributed.yaml, and a dot. The dot represents the code, the current folder. As you can see, there are no changes to the code. I'm changing only the configuration. So let's see this configuration. This configuration basically is identical to the previous one. The only difference is this one. Slots per trial 4. I want to use 4 GPUs instead of 1. And just changing this line, I don't need to change any line of the code. Create this configuration file and run distributed training. It is very easy. Using our trial API, the model has to extend our trial classes. Doing that, the product is able to manage all the infrastructure code for you. Okay, so let's run the experiment. So what happens when you submit an experiment? From your local machine, a zip file is created with all your code, and that package with the YAML configuration is sent to the master node. The master node checks for resources. For example, on cloud environments, it is also possible to use the auto-scaling capabilities. So you may have just the master node, and agents will be created on demand and will scale from 0 to any number you have configured to downscale to 0 after the experiments are trained. And this is very efficient in terms of costs. Generally speaking, the master looks for all agents that are connected. And when there are enough agents with enough GPUs, the experiment is allocated, and the infrastructure code to run the distributed experiment is automatically set up for you. So let's see our distributed experiment. Okay, it is active, distributed. Let's see. We also had a label here for just to, this was configured into the configuration file just to remember us that it runs on 4 GPUs. Okay, so here there are 2 important panels. One is the profiler. As you can see now, we are roughly 3.2 images per second. So the performance of the system has increased. And of course, in the end, we have all GPUs, 4 in these cases, that have been allocated. And for any GPU you can select, and you can see all metrics that you may be interested in. For example, the memory. When the training is distributed over several agents, you can also change the agent name. Now we have just 1 agent. And the other important aspect here is on the logs, because when you run a distributed training, for example, over 200 GPUs, you end up with 200 processes, and each process will generate logs. And you need a way to collect all those logs together. You need to centralize those logs. And here all logs are centralized. Okay. Here they are. And you can see each log now has a rank. The rank from 0 to 3, we have 3 of them. We have 4 ranks because we have 4 different GPUs. And you can also filter on the rank. This is useful when you have an issue with the GPU. It may be due to the memory or because it breaks and so on. And it simplifies the analysis. Okay, now you saw how easy it is to switch from one GPU to several GPUs. Let's see how we can optimize our model. Now the training speed has improved, but we got just a good model. We want the best model. And we want to run the hyperparameter optimization. The command is the same, that experiment create. The code is the same. You see the point. We don't need to change the code. We just need to change the configuration file. In this case, let's open the search.yaml. The configuration is almost the same you already saw. But now we want to optimize for the hyperparameters. So have a look at this. Some hyperparameters just have one value, like weight decay has a fixed value. But the learning rate and the momentum, no, they have a domain. For the momentum, we defined a domain, the minimum value 0.7 and the maximum value 0.95. For the learning rate, we have a log scale, and the domain is from 10 to -4 to 10 to -2. And we want the system to scan this space and to find the best model. And this is easily done this way. The mode now is not single because we are not training a single model. It is aggressive. Aggressive is an option for our adaptive ASHA. The adaptive ASHA is our state-of-the-art now in terms of hyperparameter optimization. It was proposed by a few students a couple of years ago, and now they have been hired by HPE because their work was very valuable. And then we just define how many experiments, how many trials actually we want to run. So we define the domain of the hyperparameters, the number of maximum trials. We are ready to run the experiment. I will show you just the result because the real training is about a couple of hours. Here it is. Okay. So what happened here? We asked the system to find the best model using 24 trials. All trials started. You see all of them here. Some of them were promoted to the next step. Others, like this one, this one, on with the low level of the metrics, were just discarded. The idea was take a small chunk of the dataset, train all models, and see what happens. And then discard all the models that, all trials that did not produce good models. All those trials were discarded. Those trials produced some models that are worthy to be trained more. So after the next stage, those models that survived receive an even bigger chunk of the dataset. And this process is repeated and so on, until we end up with one, two, or just a few models that produce the best results. Of course, this is a simple explanation, and also you see a simple configuration. The algorithm is very strong because it can cope with models that requires time to train. Actually, it runs 3 different processes, optimization processes in parallel. Now you can just see one because it is easier to follow. And the algorithm is now, I think, should be the fastest that you can find on the market. Okay. Now we optimized our model. And in the end, we got the best possible model. What we can do with this model? We want, for example, to run inference. The model has to be deployed into production and run inference. The next step after the training would be to register the model, the checkpoint, into a model. So we have a model registry here. Those are the models that we defined. We can go into our experiment, for example, this one, the distributed. Okay. We can see the checkpoint that was created and stored, the best one. And we can register this checkpoint to a model. We can create a new one, but let's assume this one. The version, you can provide the version. If you do not provide it, it is automatically added. Okay, let's go back to the model registry, pedestrian detection. Okay, this is the model, the checkpoint I registered just now. And now I can use the model by name to run some inference. Or, for example, I can also, if I want to automate this process, because it is normal to automate it, I can use the SDK. For example, I can take the experiment 471. Okay. I get the checkpoint. I check if the model exists or not. And finally, I can register using the API. And if we just want to check, there should be another one. Just now, here it is. Okay. So let's switch back to the, of course, there are a lot of other possibilities. For example, you can have all information regarding the cluster, the number of nodes, and the number of agents. You can define multiple resource pools. Defining more resource pools, you can subdivide cheap hardware with expensive hardware and reserve expensive hardware for experiments that are more important. You may have the historical usage of the cluster. So in terms of GPU hours or in terms of users, which user is using the cluster compared to the others, and so on. And the product provides a REST API that you can leverage with the SDK in order to extract some information. Also, the metrics that you see here can be extracted. And there are some Prometheus endpoints that you can use, connecting Prometheus and then using Grafana to show dashboards with those metrics. So let's go back to the slides. Okay. So the product comes into different flavors. There is the software-only version, which is the one I showed you. You have all the capabilities, hyperparameter search, distributed training, experiment tracking, user collaboration, resource management, and so on. And you can install on any system. I mean, you can install on virtual machines, on bare metal, on Kubernetes cluster, on cloud environments, where you can leverage the auto-scaling capabilities. Then there is in the middle the machine learning development system. This is a combination of hardware and software. The software is the one I already showed you. The hardware is made by our Apollos 6500s, each one with 8 GPUs. Now we support NVIDIA with the A100, but we are working to support many other accelerators like AMD or like GraphCore, for example. And those nodes are interconnected by a high-speed infinite-band network layer. This provides the best performance for distributed training. And the last product is the same software version plus a connector that allows you to run AI jobs on a Slurm cluster. And this allows you to mix HPC and AI workloads. So, as I already mentioned, the machine learning development environment is built on top of the Determined AI open source software. The open source software contains almost all features that you saw. The open source software contains the distributed training, resource management, hyperparameter optimization, experiment tracking. Basically, even the user interface the demo that I showed you was on the open source version, was not on the enterprise version. The enterprise version provides just the premium support and a couple of connectors for users. So in an enterprise, you may want to connect your users with Open ID Connect or SAML, this kind of connectors. But all the machine learning and deep learning functionalities are there inside the open source version. And as an open source component, we have a big community on Slack, more than 1,000 active users. And you may find there also the developers working for HPE. And it happens very frequently that the developers answer to questions. On GitHub, beside the code of the open source version, there are a lot of examples, a lot of code. There is a repository called Works with Determined, which is open and contains code with different kind of integrations. There is one also between Pachyderm, Determined, and Seldon that I created and provides a lot of code. And what happens is that many customers maybe prefer to start with the open source version because they can install for free, experiment, assess, see if the product is worthy, and then switch to the enterprise version after we start with they start with production. Is there any question?
Thank you very much.
Thank you. You are welcome.
Thank you very much for your report.
Thank you. Thank you. You're welcome.
You can go to the stage to the top. Yes, you need to go to the stage.
Okay.
How
Here?
No, not the stage, the biggest stage. Come with me.
Okay.
الورشة خلصت هنا صح؟ تمام. عشان بشيل الجهاز بس. تمام. أيوة. أهلا دكتورة فاطمة، حبايبي. حياك الله، يا أهلا والله. كيف حالك؟ الحمد لله، الحمد لله.
can't forget how we spent.
جزاك الله خير يا دكتورة، يا أهلا وسهلا. آمين، جزاك الله خير يا دكتورة. الحمد لله، ناس حياك الله.